Okay, so now we have to generate this 12 formulas of doom that form the CNF instance that the reduction computes, such that this formula is satisfied. All of those 12 formulas will be satisfiable, if and only if the original Turing machine has an execution on the input for which it accepts in the acceptable input. So to remind you, here is a quick recall of the variables annotation. So we listed all the transition. The jth instruction of M is going to be this transition, right? This is going to be all the information in transition. Then we have the three groups of variables. IJI is the jth instruction is being executed in time I. HHI is the head of the tape is at location H at time I. And TCHI is the tape at location H at time I has the content C. Okay, so the first claim is that the input is encoded correctly. So, well, to be more precise, first we require that the start state at time 0 is Q0, right? So the Turing machine in the beginning of the execution is at the start state. Then we require that the first n tapes input of the tape contain the input x1 to xn. And finally, we require that the rest of the tape is empty. Okay, so this is phi1. Fit the first. Now let's do the second formula. For every one, in any given point in time, only once, the machine is only in one state, right? So CQ0I says the machine is at state Q0 at time I. So we go to all the possibilities, right? Over all the letters Q in Q. For each one of them, we write the variable SQI. And we put all those, each one of them is a variable, right? It's one if it's in the state. And we take all those variables at time I and we take the O plus, right? O plus, to remind you, was this formula that says, it's a CNF formula that says all those variables, all of those variables, there is exactly one that is one. Okay, and now we take the intersection, the end of all those formulas across time, right? So any point in time, this holds that only one state is in play. Second fit, now next one. For every cell, in any point in time, there is only one value that it contains. So again, we look on the any point in time, any cell, and we look on all possible values of the cell. To remind you, TB1HI says the tape at location I at time I has the content B1, right? So we put all those variables inside an O plus, requiring that exactly one of them is true, and we take the intersection across everything. Right? So this is that. The next step, the tape head is in exactly one location, right? So you look on all the variables that tell you where the tape head is at time I, and you take an O plus of them, and then you take the intersection across time, right? Now, of course, we require that the Turing machine accept the input. So one way to say it is that we require that at time, in the end of the running time, P of X, the state of the machine is in the accept state. Alternatively, what we can do is we take the union across time, and we ask that in one of the point in time, the Turing machine is in the accept state. To remind you, you can just assume that the accept states, once you enter it, you never leave, right? So the two are really equivalent, but if you prefer the second way, then the second way it is. Okay. Similarly, we require that at any point in time, only one instruction is being executed. So I1I is the variable that is 1 if the first instruction is being executed at time I, right? Instruction, to remind you, is the transitions where we listed them. We listed all of them, and we just numbered them. So we just take all those variables at time I, and we take the O plus, and then we take the end across time. Okay, so that's easy enough. Seventh formula. I'm sure that by now you are getting tired of this nonsense, but let's plow ahead. The head can change only because the head writing something on the tape, right? So we require that so what do we require? We require that we look on across time, we look on the head, we look on any two different character, and we say the fact that the head is not at location H at time I implies that the I tape has the same value before and after. Right? Or if you want, the fact that the head is not there implies that the value have not changed. Okay, now you have to use the fact that implication A implies B is equivalent to not A or B. This is a standard logic formula, which means that if you substitute it in, you get a big CNF formula. So that's a good CNF formula. Okay, so we got a CNF formula that says the tape doesn't change on its own. There is no immaculate change of tape. Okay. Now we need to make sure the transitions are done correctly, right? So what does it mean? It means that if at time I, we decided to do transition J, the J instruction is executed, then it must be that we are in a state QJ, we are in the state that this transition starts from, right? So before you can transition, you can apply this transition, you need to be in this state, and that's what this formula guarantees, right? And again, you need to use the implies thingy to make sure that this is a CNF formula. Let's not worry about that. It's true. Okay, next. Similarly, we need to write a formula that says that the Turing machine had transitioned into a correct state. So if at time J we did transition J, then the state at time I plus 1 is QJ prime, the target state of this transition. Okay. And of course, every transition also requires the right letter to be written on the tape for the transition to happen. So we add this, saying that if we decided to do the instruction J at time I, and the head is at location I, then it must be that what written on the tape at location H at time I, this is this character BJ, which is the character that here that initiate this J transition. Right? So, and again, we take intersection across location, time, etc. Okay, we are almost done. Now we need to say that the correct symbol was written to the tape. So it's the same logic, right? If we execute command J at time I, and that is at location I, then at time I plus 1, at location H, what's written is what is in the transition. So that's not, again, this is, after you open it and so on, this is a CNF, a huge CNF formula, but still polynomial size. So everything is good. And finally, what do we need in the final thing? That the head is moving correctly, right? So again, if we execute the transition J at time R, and the head is at location H at time I, then the head must be in the right location at time I plus 1, where this is the current location, plus DJ. DJ is either plus 1, minus 1, or 0, right? And this is a version where we allow the Turing machine to stay in, the head can stay in place. So that's it. fun. We define those 12 SAT formula, you take the intersection of all of them, you get this huge CNF formula, still polynomial size in the input. Clearly it can be computed in polynomial time because computing it was pretty mundane, tedious but mundane. So we have this huge formula, and if there is a satisfying assignment, then we can fill up the matrix of execution. We can, the Turing machine has a simulation for which it accepts the input, namely there is accepting the execution, and the word indeed belongs to the language. So a satisfying assignment implies that M accepts the input X and vice versa.